Hello everyone, I'm Kadek, a PhD student from KAUS. In this talk, I'm going to show to you the results of our ongoing work on earthquake dynamics in a multiscale fracture, in collaboration with Paul Martin May, Alice Gabriel, Dimitri Garagas, and Tolma Ulrich. Fault consists of a multiscale fracture within fault damage zone. In fact, by zooming into the fault zone, the fault becomes more and more complex, and it comprises of a fracture network. And then the local stress perturbation within this fracture network might induce an earthquake of magnitude larger than 5 via fast cascade. Therefore, the hypothesis of this study will be the stress perturbation on a well-oriented fracture in the damaged zones might produce a significant earthquake via a cascading rupture. A good illustration behind dynamic cascading is shown by the following video. Suppose this domino is a fracture network, and all blocks here are a fracture that are favorable to slip, and the biggest one is the main fault. The stress perturbation on the small fracture leads to a cascade rupture and eventually trigger the main fault, for instance due to the fluid injection in geothermal area. Therefore, we conduct 3D dynamic rupture simulation among hundreds of connected multiscale fractures to capture the dynamics of the cascading rupture. Questions we want to answer are the following. Can rupture occur on favorably oriented fracture in the damage zone and then promote a runaway rupture on poorly oriented main fault? Can dynamic rupture propagate as a sustained cascade on a fracture network in the damage zone without triggering the main fault? And to answer these questions, we conduct 3 models of 3D dynamic rupture simulation by combining 824 fractures embedded with a elliptic fault plane. Model number 1 is unfavorably-oriented main fault and fracture. Model number 2, favorably-oriented fracture and main fault. And model number 3, favorably-oriented fractures and favorably-oriented main fault. In addition to that, the cascading earthquake is feasible by considering novel analytical multiscale dependence of fracture energy and fault size. More detailed study can be later found in Gabriel et al. That is still in preparation. Next, the numerical model is constructed following a statistical measure observed in field observation. In this study, we choose geological interpretation of fracture in the damage zone close to a elliptic fault. The fracture density and fracture size follow a power law decay. And then you can see here the fracture density close to the main fault is lower than a power law function to avoid high computational cost. In this study, we consider 2 dominant strike orientation, north 120 east for fracture family number 1 and north 20 east for fracture family number 2 with standard deviation of 10 degrees. The spatial distribution of our simulated fracture network in map view can be seen from this figure here. The elliptic main plane is constructed with depth-dependent dip, varies from 40 degrees up to 85 degrees. The fracture plane output is inserted into a numerical solver sisal. And then we also use laboratory-based rate and state with strong velocity weakening friction law with friction parameter chosen to generate a realistic stress drop and dynamic frictional resistance. Note that for all simulation, the rupture nucleation is generated dynamically with overstress volume, which includes the main fault and subset of fractures with a radius of 300 meters. Next, to show the result, we use an exploding view to better visualize the slip rate evolution. As you can see, this is the original view. And then this is the exploding view that is represented by 3.5 times the original fracture distance. Next, let's talk about the results. For model number 1, where the fractures and the manifold are unfavorably oriented. On the left, you will see the slip evolution, whereas on the right, you will see the slip rate evolution. Again, the rupture starts in the middle of the manifold here. The subset of fracture and manifold inside the nucleation volume are unfavorably oriented, and hence minimal self-sustained rupture is generated. The slip is also confined inside the nucleation volumes. Similar as previous model, the rupture here starts in the middle of the manifold with subset of fracture, and then the rupture propagates zigzagging alternately through two different fracture families and generates a cascading rupture. As you also can see on the slip rate evolution here, the rupture stops either abruptly at a fracture edge or self-arrested on a fracture with less favorable to slip. The stress transfer onto the neighboring fractures is due to two mechanisms. The first, dynamic branching, which involves the connected fractures, and second, dynamic jumping, which involves unconnected but close in distance. Interestingly, as you can see on the slip evolution here, although the cascades is mechanically feasible, it still cannot trigger a runaway rupture on the manifold. Slip on the manifold is only transient at the manifold and fracture intersection. Let's move on to model number 3, where the fractures are poorly oriented but the manifold are favorably oriented. Again, the rupture starts in the middle of the manifold, and then it propagates bilaterally to the east and to the west relative to the hypocenter. And it activates the off-fault fracture which are initially unfavorable to slip. The off-fault, as you can see here, the off-fault fractures are advancing or prohibiting rupture from evolution, therefore resulting in heterogeneous slip distribution similar to what we found in rough fault case, although the manifold considered here is smooth. From the three model considered before, now let's compare the kinematics of the earthquake source through new parameter that we call a cascading speed. The cascading speed is defined as apparent cascading rupture speed along the fracture network within the fault event zone. The cascading speed can be interpreted as a rupture speed, average rupture speed from a macro scale view, or if one sees the rupture as a line source. In this figure, the cascading speed is shown by the black solid line, as this figure in the middle. The dots and triangle are fracture family 1 and fracture family 2. Then different color here represent the location of the fracture with respect to the hypocenter. This rectangle here is the manifold with a solid line exhibit the rupture time contour. Now let's see the model number 1. This M1 shows a limited slip on the manifold plane and only a small amount of slip fractures that is occurred only in one family. In model number 2, one can see the progress of fracture activation with time. Interestingly, the rupture is also progressing back to the hypocenter. As I mentioned before, the cascading rupture cannot trigger a runaway rupture on the main fault plane, but only a limited transient slip at fault fracture intersection, and hence one can observe this patchy rupture time contour that is similar to the intersection between fracture and the main fault. In contrast, model number 3 shows bilateral rupture. Considering a smooth surface that we have considered, the rupture contour does not show a typical slip, but rather similar slip as we can find in a rough surface. Now, if one sees the cascading speed, model number 2 has a lower cascading speed than model number 3. The cascading speed of this model 3 is similar to the overall average rupture speed calculated from the fault size over the rupture time. The slower cascading speed for model number 2 is incorroborate with a slow average rupture speed if one consider the earthquake source as a line source. Probably this slow average rupture speed that one observed during an earthquake is actually considered as a cascading speed through a fracture network in the damage zone. In conclusion, we model 3D dynamic earthquake rupture as a cascades over a network of several hundreds fracture in the damage zone. Dynamic rupture cannot propagate away from the nucleation zone in model number 1, or it cannot propagate away if the main fault and fracture are unfavorably oriented. Cascading rupture across the fault network fails to activate a runaway rupture on the main fault plane. It only produces a transient slip at fault fracture intersection. And finally, the runaway rupture on the main fault generates slip even on unfavorably oriented or fault fractures. If you have further questions, please don't hesitate to contact me and email me at kadek.palgunadi@kaus.edu.sa. Thank you for listening.